Hey everyone, and welcome. Have you ever stopped to wonder what's going on behind the scenes making our digital world feel so snappy and organized? Well, today, we're going to pull back the curtain on one of the most powerful, yet kind of invisible structures in all of computer science, the tree. It's an idea that's as elegant as it is absolutely essential, so let's jump right in.
I mean, really think about it for a second. You type in a search and bam, there's your file. You're not sitting there for minutes while your computer grinds away, checking every single thing one by one. So how is that even possible? It feels like some kind of digital magic, but it's not magic. It's just really, really brilliant design.
And the secret? It's a data structure that's actually inspired by nature, mimicking a family tree or, the branches of an actual tree. So it's called, not very surprisingly, a tree. The file system on your computer is the perfect example. You've got your main drive, that's the trunk, and it branches out into folders, which then branch out into more folders and files. It is all about hierarchy. So here's our game plan. We're going to start with the absolute basics of what a tree even is, and then we'll break down its anatomy. After that, we'll get to the really cool part, its superpower for searching. Then we'll look at its biggest challenge, and finally, we'll go on a hunt to see where these things are hiding in the tech you use every single day.
All right, first up, what is a tree in the world of computer science? At its very heart, it's all about one thing, representing relationships and structure. So a tree is basically a collection of points, which we call nodes, that are connected by lines we call edges. But here's the one golden rule. You can never follow the edges and wind up back where you started. There are no loops, no cycles. And that simple rule is what lets it perfectly model hierarchical stuff, like a company's org chart, or, just like we saw, your computer's file system. Okay, so to really understand trees, we kind of have to learn how to speak their language. The good news is the terms are super intuitive. They borrow a lot from family trees, which makes it way easier. Okay, so every single tree has a beginning, right? We call that the root. It's at the very top. Each point of data is just called a node. Now, any node that has other nodes branching off below it is a parent, and those branches lead to its children. And finally, you have the nodes at the very, very end of any branch. The ones with no kids of their own, we call those leaves. See? Simple enough. And here's how it all clicks together visually. You've got the root node sitting right at the top, which then branches out. And see that dotted line there? That shows something really cool. Any node and all of its descendants can basically be seen as their own little mini subtree. This recursive, self-similar pattern is what makes trees so incredibly powerful and flexible. Okay, so we know what a tree is. But now let's talk about what makes one specific type of tree just so unbelievably useful. We're going to zoom in on a special kind called the binary search tree, or BST for short, which has a genuine superpower. Now, this isn't just any old tree. A binary search tree is an ordered tree. It organizes all of its data based on one strict but totally brilliant rule. And this one rule is the entire secret behind its insane speed. And here it is, it's this simple. For any node you're on, everything in the subtree to its left is smaller, and everything in the subtree to its right is larger. So when you're searching, you just start at the root and ask one question. Is what I'm looking for bigger or smaller? Smaller, go left. Bigger, go right. With every single step, you're literally throwing away half of the remaining data. This little table shows just how massive that difference is. A linear search is like looking for a name in a phone book that isn't alphabetized. You'd have to check every single name, one by one. In computer science terms, we call that O of n, meaning the search time grows in a straight line with the number of items. But a tree search is O of log n. Because you keep chopping the problem in half, the search time barely goes up, even if you add millions of items. So just how fast is that? Get this. To find one specific item in a pile of over 1 million items, a nicely structured binary search tree would only take about 20 steps. Not 1 million. Not 1,000, 20. That is the jaw-dropping power of O of log n. But of course, there's always a catch, right? That incredible speed only works if the tree keeps its nice, bushy shape. If it gets all lopsided, its superpower just disappears. So on the left here, we see a beautiful, balanced tree. It's short, it's wide, perfect for searching. But look at the tree on the right. Yikes. If you add data in an already sorted order, like 1, then 2, then 3, 4, 5, the tree turns into this long, spindly chain. It's not really a tree anymore. It's basically just a list.
And searching a list puts us right back at that slow, O of N, check every single item slog. All that beautiful efficiency is just gone.
So, keeping that balance is absolutely crucial. To solve this problem, some brilliant minds develop what are called self-balancing trees. You might hear names like AFL trees or red-black trees. They have these clever built-in rules that automatically do little rotations and adjustments whenever you add or remove something. It costs a tiny bit of work each time, but that little investment guarantees the tree never gets lopsided and stays super fast forever.
All right, now for the big payoff. We've gone through all the theory, but where do you actually run into these amazing structures? The real answer is, well, everywhere.
We started here, and it's the most classic example there is. Every single time you click through folders on your computer, you are quite literally walking down the branches of a tree data structure. Ever wonder how a massive database, like for a bank or a big website, can find your specific record in a fraction of a second? The answer is usually a special, beefed-up kind of tree called a B tree. It's optimized for systems that need to read big chunks of data from a hard drive, making those searches lightning fast. And the list just keeps going. You know that autocomplete feature in your search bar? That's powered by a special tree called a trie. AI models that have to make predictions, they often use decision trees. Even the internet itself uses tree-like structures to figure out the best way to route traffic across the planet. They are truly the unsung heroes of our digital world. And this quote from our source material just nails it. It sums it all up perfectly. When you've got a mountain of data and you need to find things in it over and over again really fast, trees are just one of the most elegant and efficient tools we've got. So in the end, trees are this secret language for organizing information, an idea we borrowed directly from the natural world to bring order to digital chaos. It really makes you wonder, doesn't it? What other brilliant ideas are hiding in plain sight, borrowed from nature to build the technology we use every day? Thanks so much for joining me.